Ladies and gentlemen, dames en heren, dear colleagues, geachte collega's, welcome to the public doctoral defense of Douw Marx. I declare the session for open. Douw Marx obtained a Master of Engineering in Mechanical Engineering at the University of Pretoria in South Africa. Douw Marx also has submitted now a thesis to the Faculty of Engineering Sciences entitled Fault Detection in Rotating Machinery Using Domain Knowledge and Reference Data. This as part of the requirements for the degree of Doctor of Engineering Science. Douw Marx will now proceed to defend his thesis. You're invited to give a presentation of approximately 45 minutes about your work, and following your presentation, there will be time to discuss your work with the members of the examination board and with the audience. The floor is yours.
Thank you very much, Mr. Chairman. Can you hear me well? So I've always wanted to go and live in the desert. And recently I got the opportunity to do just that. And I went to Death Valley in the Nevada desert. And this is quite a sort of barren and desolate place in the middle of nowhere. And this is where I stayed one night, right there. And the next morning, when I woke up in the middle of nowhere and I wanted to go somewhere, I saw this sign in the car. The fault detection system in this car was telling me that I had a flat tire in the middle of nowhere. And so I got out and I was very relieved to see that I did not have a flat tire. Fault detection systems make mistakes all the time, and this was just a false alarm. So I could head back, and here I am today to present my thesis on fault detection in rotating machinery using domain knowledge and reference data. So in this work, we show that we can detect faults without faulty data using domain knowledge and reference data. So I'll start with the introduction, where we'll look at the turbo machinery example, and then I'll present 3 parts of our work, a selection of our work, and all of them deal with this idea of making use of reference data and domain knowledge. So we don't want to detect faults in car tires. We want to detect faults in critical infrastructure, like wind turbines or mining equipment, or this turbo engine, which we'll cover now as a small example. So we also don't measure pressure. Instead, we measure vibration. So we can't look inside the machine, so we need to measure it in a different way. And so that's why we use accelerometers, which you see here on the left, to make these measurements. On the right, you see this machine for which we will see a measurement right now. So this is a measurement from this turbo engine we just saw. So who of you think this is faulty? Maybe just raise your hand quickly. So how many of you think this is faulty? 1, 2, 3, there's maybe 6. So 6 people think it's faulty. How about this one? Sorry, this one is actually normal. So you're wrong, sorry. Raise your hands. Who of you think this one is faulty? 1, 2, 3, 4, maybe 5 again. And this one is actually faulty, right? But the point I'm trying to make here is that it's not so easy to distinguish between normal and faulty signals that we measured from a machine. These two were the sort of exclamation points. Those are faulty, while the other ones are normal. So we have this task of translating this signal to a number that stands in for its health. So we need a number that tells us how faulty a given machine is. So we need to translate this measurement X into a health indicator H. And we need to change whatever is in that box to create a health indicator. So maybe 6 people raised their hands. That's an example of a health indicator. You observed a signal and we translated that into a number. But of course, we don't have an audience to diagnose all our signals, so we use signal processing methods. An example is maybe the RMS, indicator of cyclostationarity, the reconstruction error of an autoencoder. All of these are examples of ways in which we can generate health indicators. And this whole body of work deals with designing that little box, creating different methods that can detect faults in machines. But before we get into these different methods, why does it matter? Why does it make sense to invest time in making fault detection methods better? This has a lot to do with the costs associated with mistakes. So when I was in the desert and I thought I had a flat tire, that was kind of anxiety-inducing. You know, I thought I was going to be in the desert for the rest of my life. But a different kind of mistake that could happen is if the fault detection system does not detect there's a fault. So here on the right-hand side, if you say everything is fine, but the machine is broken, that's also a dangerous kind of mistake to make. Here on the right-hand side of the slide, there is just a demonstration to show how good detection can lead to reduced cost. So in the bottom XY plane, we have this ROC curve, which I'll discuss later in more detail. But what you can know for now is that our best detection is achieved when that blue curve passes through the top left line. And as a consequence, also, the costs are as low as possible. So that's why we want to improve our fault detection methods. But there's also a bit of a catch. And that is that we don't have access to any faulty data. So we're only allowed to use data from the machine that is measured when it was in a normal condition, and we're allowed to use our knowledge of, our domain knowledge of how machines tend to fail. So that's a lot like trying to find a needle in a haystack, even if you've never seen a needle. I've never seen a needle. That sucks, needless to say. But hey, I know my needles, and just look at all this hay. So we've got some domain knowledge, which is our knowledge of needles. You know, I know my needles. We've got some reference data. We have all this data we measured at the beginning of the machine, but we've never seen any examples of faulty behavior. So that's the constraints in which we need to work. And we propose two kind of streams, two kinds of ways of thinking of solving this problem. On the left-hand side, we have data-driven signal processing methods. And in this case, we take some data and add it to a more traditional signal processing approach. So we have a more domain knowledge heavy method, but we want to integrate data into that. And the other way of looking at it is that we take our domain knowledge from signal processing and we want to add that to flexible, unsupervised models that are more data driven. And so these are the contributions we make in this work, and they range from replicating signal processing methods with deep learning blocks to regularizing unsupervised deep learning networks with domain knowledge. But for this presentation, we're going to focus on these three sections in red. And yeah, let's jump right in and start with this filter selection approach. So this filter selection approach is firmly rooted in the first part of, or the first, let's say the A part of the research. So this is where we have a more domain knowledge heavy method, and we try to add some data into this. We want to trust our data. And so just a little background on this. Many problems in fault detection involve the maximization of a fault metric. So it's not, you don't just generate the fault metric like you guys raising your hands. There's a optimization step in the middle. So you might look at a certain part of the signal, for example. But examples in this include blind tick evolution, grams and frequency plane methods, and window selection. All of these solve an optimization problem on the signal you currently get. So you get a new signal, you solve an optimization problem as a function of some parameters, and you want to reach the maximum. But the problem with this is that if you blindly maximize a metric, that can lead to false alarms and misdetections. So in this work, we propose to use reference data as a way to regularize this, to avoid fitting to an objective that can lead to false alarms and misdetections. The application we present here is for filter selection. So filtering a signal to extract certain frequencies that are most useful for detecting the fault. So this is a conventional formulation where our health indicator H that comes out is the result of an optimization problem, where you have the optimal parameter theta here. And so we want to generate a health indicator using the filter parameters that maximize the fault metric. In this case, this objective consists of a filtering step where the signal goes in, it gets filtered, and we calculate a fault metric on that filtered signal. And we want to generate a health indicator that using the filter parameters that maximize the fault metric. The question we try to answer is, should we just blindly maximize this objective, or is there a better way to do it? And we claim that using reference data is the solution here. So on the left is this baseline approach, which I just introduced, which is the conventional approach of filtering and calculating a fault metric. But what we then propose is a small change in this approach where we kind of normalize this indicator. So here on the top right, you can see it's the same as here on the left, but now we subtract the mean and divide by the standard deviation of the reference data. It's a lot like Z-scoring. But the thing here is that this mean and standard deviation is also a function of the filter parameters theta. So this whole sort of Z-scoring is driven by the optimization parameters theta, which in our approach is the filter parameters. So on the left, we just blindly maximize, and on the right, we maximize the discrepancy. We want to separate the faulty data as far away from the normal data as possible. Here you can see that in a graphical form. Here in the baseline approach, the signal goes in, it gets filtered, it produces a fault metric, and then we iterate until that is maximized. On the right, we have the same story here in this part at least, but we additionally have a reference set that we pass through the filter and calculate the fault metrics. We also have to evaluate this method, and so we use different fault metrics to optimize for. So you can choose an arbitrary metric after the filtering step, but there are some that have been proven to work well, and we choose the kurtosis, the negative entropy of the squared envelope spectrum, and the L2, L1 norm of the squared envelope spectrum. We don't aim to introduce new metrics here, we just want to evaluate if our optimization method is performing well. At the same time, we also use different filters. We use a simple 2-parameter first filter. Here on the x-axis we have frequency, so this filter basically just tells you which frequencies are being let through. And on the right-hand side, we have a more intricate filter that can resemble arbitrary frequency responses. And this is just a multi-parameter FIR filter. But let's start with an example for the single-parameter FIR filter so we can just understand how this approach works. Here we see a similar kind of signal we saw in the beginning, where you have a faulty condition and a reference condition. And the faulty condition has this additional weak fault component that is added to it. So it's difficult to distinguish them, but we're going to use this as a benchmark for our method. So now we're going to look at 2 of these plots, this one and this one for the discrepancy. But I'll explain the plot using this baseline approach. So what we see here is on the x-axis is the filter parameter. In this case, it's only one parameter. It's the filter center frequency as a fraction of the Nyquist. So this is our filter parameter. And we're optimizing this at each new signal. So we get a new signal x. We plot this objective function for that signal x. So each trace, each red and green trace represent an objective function for a given measurement. And then we optimize that. So here, let's say we take the maximum and we transfer that maximum over here on the right-hand side as our health indicator, because that's how we define it. We defined the maximum as our health indicator. But so in this case, for the baseline approach, you can see that for the reference data in green, so the normal data in green and the faulty data in red, there's an overlap. So that means that our detection is not very successful. It's not easy to set a threshold and say everything above this is faulty. Conversely, for the discrepancy method, you can see that the fact that we encourage the method to separate the evaluated measurement far away from the reference samples allows us to have a better separation of the faulty data and the normal data. And this is also kind of confirmed if we look at the receiver operating characteristic curve. So this is the curve we saw in the beginning quickly, but here I'll explain it in a little bit more detail. So it gives you the trade-off between the true positives, so the probability of detecting a fault, versus the false positive rate, which is the probability of false alarm. And you can see that for the baseline approach, we are performing very close to random guessing. So there's not really we're not really detecting things very well. But for the discrepancy approach, we do not really have to trade much false alarms to get a good detection performance. So it seems that adding this reference data, at least in this example, gets us better detection. But of course, we also want to evaluate on experimental data. So we're going to look now at multi-parameter FIR filters, so the kind of filters that are more conventionally applied. We're going to look at these examples for 2 experimental data sets. These are the results, and specifically what these are showing is each dot you see on this plot represents a data set. So a data set from a certain operating condition or a fault mode, or a different type of data set. And so a given data set might have 15 normal signals, 30 normal signals and 30 faulty signals, and then we evaluate how well can we detect these signals. The metric we use to quantify how well we're doing is the area under the ROC curve. So we just looked at the ROC curve, and it turns out that if you use the area under that curve, it's a nice way to quantify how well you're detecting. It ranges between 0 and 1. Okay, so what we're then plotting is on the y-axis, we plot the performance for the discrepancy method, and on the x-axis, we plot the performance for the baseline method. So if both the baseline and the discrepancy method were performing equally well, these dots would lie on the diagonal line here. But you can see that in the majority of the cases, the dots lie above the diagonal line, and that implies that the discrepancy method tends to outperform the baseline method for that given data set. We also then repeat that for different fault metrics, so that's kurtosis, the squared envelope spectrum, negentropy, and the squared envelope spectrum L2, L1 norm. And the same is true for different filter orders. And so across the board, it seems that this discrepancy method is a good idea. It improves our fault detection. So to summarize, we propose a filter-based fault detection method, and it can be improved by adding reference data in the optimization problem. We compare over different data sets and fault metrics and filter types. And in general, this discrepancy method tends to outperform the baseline method. It needs to be mentioned that we need to apply this filtering also to a whole reference data set, so the compute cost might scale linearly with that. So there's benefits and costs. So that's the first part done. Let's move on to the second section. In the first part, we were more domain knowledge heavy, so we were using our needle knowledge. But now we move to a more data-driven side, so the right-hand side of this plot, and we are going to try to integrate our domain knowledge into an unsupervised detection framework. So in a more data-driven world. So when I say unsupervised in this talk, I mean we don't have access to any faulty data. Now, other people might call it semi-supervised, since we actually know that the normal data we have, the hay we have, is from a normal condition. So we technically have labels, but I call it unsupervised to avoid confusion with other uses of semi-supervised that use faulty data. So these unsupervised approaches, like autoencoders and deep support vector data description, and so on, they don't incorporate knowledge of the expected fault behavior. So they might be able to detect any kind of deviation from normal conditions, but they are not well tuned to fault behavior that we've learned over many years how faults behave. So we want to ask, can we add domain knowledge-based regularizations into these unsupervised data-driven methods to improve their performance? Specifically in this part, we're going to cover the case where we have frequency domain data as input or engineering features as input. In my thesis, we also look at using time series data directly, but we won't cover that today. So if we say we want to add domain knowledge, we need to somehow prescribe our domain knowledge. We need to tell the unsupervised model what we know. And the way that we do that is for the frequency domain data is we add triangular peaks at the fault frequencies that we expect in a faulty machine. So in machines, we know the geometry of the machine often, and that allows us to deduce the expected fault frequencies. And that is what we indicate here in the as domain knowledge. Similarly, we can calculate engineering features like RMS, kurtosis, and crest factor, and we all expect them to increase under faulty conditions. And so that's also a form of domain knowledge that we impose in this work. So there are many sort of unsupervised deep learning architectures that this could apply to, but in this work we use a simple autoencoder. An autoencoder tries to distill the crux of the data from a high dimension. So it's kind of like taking all of that hay and baling it into a small compact representation. And so the way we do that is by taking the input data X and compressing it to a lower dimension. But then the key is to force the network to reconstruct its input again. So you are acquiring the network to regenerate its input from a smaller latent representation Z. And that allows you to learn a nice compact representation of the data. But so that's the conventional approach of doing that, and those compact data, you want to ultimately use them for fault detection. But so what we propose here is to see if we can communicate our expectation of what faulty behavior looks like. We want to communicate that to these latent features. Can we learn better latent feature Z by adding our domain knowledge? And when I say better, I mean better for fault detection. And so the way that we propose to do that is to add a regularization that constrains the input sensitivities of the encoder. So we can calculate the Jacobian, so the sensitivities of this latent features with respect to the input. We can calculate that thanks to automatic differentiation. And we are going to design a loss function that ensures that this directional derivative, so the agreement between the sensitivities between of the input sensitivities and our domain knowledge, that agreement needs to be big. So this is this loss function that we design, and it encourages the network to learn sensitivities that are consistent with our expected domain knowledge. We then add this regularization term to the conventional loss. So this left term is the conventional reconstruction loss, which encourages an informative latent representation. And the right hand part is this regularization we add that encourages a consistency with the domain knowledge. So does it work? The way that we evaluate it then is to check if these latent features that we learn are useful for fault detection. And the way we measure whether it's useful for fault detection is to use the Mahalanobis distance as a health indicator. So we've got these fancy latent features, and now we measure the distance from these latent features in a new sample. That's what we use as a health indicator. And we're going to compare the conventional model that doesn't have the fancy regularization and the proposed model. We're going to compare those two. We're going to use these two data sets, also with different operating conditions and different fault modes, and also different signal-to-noise ratios in this case. We're going to look at a similar plot we just looked at. With the y-axis, we will be comparing our proposed method, and on the x-axis, we'll have the conventional autoencoder without regularization. The only difference here, the markers still represent a data set. The only difference now is that we report the median score over 10 trials, since these models have some randomness when you train them. Okay, let's have a look at the results. So at the top row, you see the results for the one data set, and at the bottom row for the other data set. And you've got in the first column is for engineering features as input, so RMS, kurtosis, and so on. And on the right-hand side, you have for the frequency domain data, which is the envelope spectrum, as input. Here you can see in the top right corner, the proposed method tends to outperform the baseline method quite consistently. That's also true for this data set, but for in the engineering features data set, it's maybe not as obvious. We still tend to outperform it, but I won't bet the farm on it. So it tends to work better for these high-dimensional examples, it seems. So unsupervised models can be regularized using domain knowledge to learn latent features that are suitable for fault detection. And in our experiments, at least, this domain knowledge we added to our regularized autoencoder improved the median receiver operating characteristic curves area for the majority of the tests that we conducted. This brings me then to the final section that we'll cover today. And that is using signal processing gradients for improved detection. And this is also in the more haystack side of things, the more the data side of things, where we try to improve our detection this way. So this is what I indicate with the slide. We're dealing now here with the right-hand side, domain knowledge-driven unsupervised methods. So this work comes from the question, can signal processing gradients be useful to unsupervised methods? So we have these signal processing pipelines that have been developed through years, but what we want to ask is, can the sensitivities of signal processing gradients, does that count as useful domain knowledge? Is that needle knowledge that we can use? And I'll like to show you like an example of what the gradient of a signal processing method looks like. So here's a simple signal processing pipeline where a signal goes in, we've bandpass filtered it, and we then calculate the kurtosis of this. We also add the log to sort of keep it tame a little, so it doesn't it's not too nonlinear. And we're going to calculate the signal processing, the gradient of this. The nice thing is that with modern automatic differentiation frameworks, we can conveniently calculate the derivative of arbitrarily complex signal processing pipelines. So this is what it looks like. In the top left, you see the signal that we're taking the signal, we're plugging it through the signal processing pipeline, and we're now taking the derivative, the input-output derivative of the signal processing pipeline. And what you see here at the bottom is this gradient we just calculated. So what does it mean? Here you can see there is lots of things going on. There are big changes, and what that means is that if you were to change this reference measurement, this normal measurement at the top, if you were to move these sample points around, it will have an adverse effect on your signal processing indicator. And we can also see that when we take the frequency domain representation of this gradient, so here on the right-hand side, and you can see that all of the energy is concentrated in this frequency band, which also happens to be the frequency band that we bandpass filtered around. So this tells you that any changes in that frequency band is what will most adversely affect the signal processing indicator, which makes sense. So the question is that useful to us? Is these gradients, calculating these gradients, can it be useful to us? And so the simplest way that we can test that maybe is to apply it in an established framework for detection, namely subspace detectors. So subspace detectors is a method for detecting signals that assumes a certain signal subspace H, so a certain set of components that the signal consists of, in some noise, in noise W. And the detection is then based on the generalized likelihood ratio test. But what is important for our investigation is that the health indicator H is calculated in this way here at the end. But this signal subspace, big H, is not known to us. And so what we claim is that you can extract this big H from the signal processing gradients. So we want to answer the question, are signal processing gradients useful for detection? And we test that using this subspace detectors where we extract this signal subspace from our signal processing gradients. So how do we do that? Here's just a demonstration. Suppose we have a very small signal, only 2 samples. We've looked at long signals with thousands of samples, but let's say our signal only has 2 samples, which is not a very practical signal, but it's good for explanation. So let's say the green dots here, those are the normal signal, the reference signals, and the red is the faulty signals. They are not observed, but we include them here just for illustration. And then the surface you see here is the signal processing indicator. Our signal goes in and out comes a signal processing indicator. And if this signal processing method is useful at all, it will increase towards the faulty condition. But so what we then do is we calculate the gradients of the signal processing pipeline, which is what's indicated with these little black arrows. They point the direction in which the signal processing method will increase the most. What we then do is we aggregate all of these signal processing gradients into this big matrix G, and we calculate the singular value decomposition of all those gradients. And so the purpose of that is to extract the principal direction of these gradients. Those are the directions where the gradients have the greatest variability. So we use, as a signal subspace H, we use the directions in which we expect faulty behavior to occur. So the direction of where the signal processing indicator will most adversely be affected. We evaluate this method on 3 data sets. The first one is from is a simulated rotating machinery data set that is kind of similar to what we looked at earlier, a bearing data set, and then a end-of-line vehicle data set. So where you want to determine whether a vehicle that has just been produced has annoying sound in it. And so that's also a detection problem. What's maybe interesting in this work is that we use different signal processing pipelines that are appropriate for each of the different data sets. So each data set is a unique machine with a unique domain knowledge, and so we have an appropriate signal processing pipeline for that. But what is nice about automatic differentiation frameworks is that we can differentiate conveniently through all of these signal processing pipelines and calculate their gradients. Then now we're proposing this method. We need to compare it with some baselines because we're adding some data-driven side and we're adding a signal processing side. So we need to compare with strictly signal processing methods and unsupervised methods. We compare, since this subspace detector framework is a linear framework, we're also comparing with other linear models here. So the unsupervised models is the Mahalanobis distance and reconstruction-based principal component analysis. And then our method now here is the one in red, but also just as a sanity check, we add a random subspace detector. So if H was random, how well would we do? That brings us to this result on the simulated machinery data. So this is the ROC curve again. We want to be close to this top left corner. That is the purpose. So we have the black line is our proposed method, which tends to outperform the other methods in this example. In the second line is the signal processing indicator, and then we have 2 unsupervised methods, which is the red reconstruction error detector and the green Mahalanobis distance detector. And so in this example, our proposed method performs the other ones. For the IMS bearing data set, the results are not as rosy. Our method performs on par with other methods, except for example in this case where we perform worse. But what's maybe interesting here is that our method is the black method. In case you forgot, what's maybe interesting here is that the blue line represents the signal processing indicator, and so here the signal processing indicator is performing very poorly. It is performing worse than random guessing. So what's maybe interesting about this approach is that even if your domain knowledge is wrong, you can still achieve reasonable performance. The final data set is the vehicle data set. Here our method wins all other methods in this particular vehicle, and in this vehicle it does quite well, but it's not as good as the signal processing method on its own. But keep in mind that your signal processing method might be wrong, and then you would have had to deal with maybe performance that's like this. Okay, so to summarize this section, signal processing gradients can be useful for fault detection, and we demonstrate that using a subspace detector where the signal processing gradients are used to approximate the signal subspace. And this method tends to perform on par with other baseline methods, and it also seems to not be as adversely affected by poor signal processing pipelines. This brings me to the conclusion of this talk. So we started out in the desert, wondering how we can avoid these kind of false alarms and misdetections. And we work under this constraint that we don't have access to any faulty data. So the question then becomes, how can we use reference data and domain knowledge for improved fault detection? And we look at these two kind of ways, two perspectives of doing that. Adding data into more domain knowledge heavy approaches. And on the other side, using adding domain knowledge to unsupervised methods. And so in our presentation today, we looked at adding reference data into filter selection problems. So improving the filter detection when using filters. And on the right-hand side, we added regularization to unsupervised fault detection methods and looked into the uses of signal processing gradient for informative fault detection. Of course, there's lots of room for future work, and I also refer you to the thesis in that regard. But maybe for the work we discussed today, for the filter selection approach, where we use reference data, our tests were conducted in stationary operating conditions. So that means that the rotation speed of the machine does not vary. And a possible extension of this work can be to bin the reference data in certain operating regimes, such that you can still detect faults even if the operating condition changes. For the regularization-based approaches, there's no reason that we have to apply it to an autoencoder like we did today. It's also possible to extend that to all various kinds of other unsupervised methods like generative adversarial networks and even today's diffusion models. And then finally, the signal processing gradients that it seems sort of, a happy coincidence is that they can also be useful for troubleshooting your signal processing methods. You can, if you have some strange nonlinearities or windowing effects, it can be useful for pointing that out to you. So this is the end of my presentation. Hopefully this research can help to make our fault detection methods more robust and reliable, so that when we actually get a notification that something is broken, that it is actually broken. Yeah. Over to you.
Okay. Now we can move on to the question part of this session. And let me first introduce the members of the jury. On the far right, we have Professor Anthony from the Laboratoire Vibration Acoustique from the Université de Lyon in France. Then we have Professor Sophie van Hoeke from the Department of Electronics and Information Systems from Ghent University. Then after that, we have Professor Johan Suikens from the Department of Electrical Engineering. And then we come to Professor Frank Naats, who is also from the Department of Mechanical Engineering. And finally, the promoter, Professor Konstantinos Grillias from the Department of Electrical Engineering. Myself, my name is Dirk van Kompenol. I'm the chair of the jury. I'm just here to bring everything together. I will now pass the word to Professor Anthony.
Thank you, Mr. President. Thank you, Douw, for this nice presentation. So it was very comprehensive. At the same time, you selected only some material that you produced during your PhD. It was a nice selection that ends up with a story that is well organized. So, as you mentioned, you started from the desert, and then you ended up with something which is well structured, a nice construction at the end. So yes, I have a few questions. So starting with your chapter on filter parameter selection, so the single processing approach is very much based on it's essentially based on reference data. That's the key point. Could you give some guidelines as how to select these reference data, as they must be very important? I guess they must reflect the diversity of operating conditions that the user expects in normal condition. So what are your guidelines to select these data, and what is the amount of data also that is needed?
Very good. Thank you, Prof. I think that's an important question because our assumptions are that we have all these reference, we call it reference data because it is, we don't know for sure that it is normal in the normal condition. So it's quite important that all of the data we use is actually in a normal condition, because it could be that faulty data leaks into our set of reference data, and then our system will not perform as intended, because if there's a lot of faulty data inside our reference samples, then we will no longer be able to map our new measurement far away if it is also from a faulty condition. But maybe closer to your question, we should select our reference data that such that it is representative of our test conditions. So we want to select, we typically would measure our reference data during the beginning of the lifetime of the machine and ensure that that captures all of the varying operating conditions that we will encounter later on, and then at a certain point cut off that reference data and use that when evaluating. Does that answer your question?
Yes, okay. And what about the amount? I have in mind a figure from your manuscript where you showed the improvement with the amount of data, and as far as I remember, the needed amounts in terms of number of signals was quite important.
Yes, that's true. That's true. Yeah. That makes sense that you bring it up. So if you plot the, okay, so we've got this reference data set, and we might have 30 sigils or so, but we can vary that number. And as we can plot the performance, so let's say the area under ROC curve metric, and it sort of grows logarithmically, and at some point it converges. So it is quite important to use a sufficient amount of reference data so that you achieve this point of convergence. Yeah.
Okay, so that's important information for the user. There are many databases which are publicly available where the number of reference data is very limited. Sometimes there are one or two signals that represents the healthy condition. And so would your method apply in such case, or do we need more?
I think the short answer is we probably need more, but I think the point we need to prove here is that we outperform the baseline approach. So even if, and I can't tell that to you with certainty that with one reference signal we're going to beat the baseline approach, but that's what we need to test. If we have low data, it might not matter that much if it's better than just the baseline approach of maximizing. Yeah.
Okay. Yeah, this is clear. Okay, thank you. So when listening to your presentation today, and again, you tried to tell a story, so you showed a different facet of your work, and it struck me that actually two of the approaches that you proposed are, it seems to me, are antagonist. So I'm trying to explain, and correct me if I'm wrong. That's my question. The The first one is, in my understanding, to control the probability of false alarm. So you use reference data in order to control or reduce the probability of false alarm. And the other approaches, which you call the unsupervised and based on knowledge, on domain knowledge, try to use the or maximize the sensitivity based on the gradient of the health indicator with respect to the signal when we observe a certain type of fault. And in my understanding, this is maximizing the probability of detection. So correct me if I'm wrong, but these two approaches are antagonists in the sense that one's try to minimize the probability of false alarm. I'm using the statistical description. And the other one is trying to maximize the probability of detection. And that's antagonist in the sense that if necessarily, if you try to minimize one, it will also have an effect on the other one. What is your point of view on this? And why not trying to involve the two approaches together in the same problem?
Okay, I think that's a very interesting question because the way I view the fault detection problem is that we want to get closer to something like the Neyman-Pearson detector, where we have a likelihood ratio test of the probability of being faulty and probability of being healthy. But in our problem, we don't have access to any of these probability distributions. We don't have access to the healthy data distribution that we can approximate maybe from the reference data, and we also don't have access of the faulty data distribution that we have to speculate on using our domain knowledge. So these two ways of looking at things, starting from the domain knowledge and adding data, and on the other side, starting from the data and adding domain knowledge, those two ways of looking at the world, I view as ways of getting closer to this idealized Neyman-Pearson detector, which we don't have access to. And then the second part of your question, I think you hinted at sort of combining them in some way, but I think that is what we already are doing. So I think when we first approach this problem, you see these two fields. You see a more domain knowledge heavy signal processing field, and you see a more AI heavy unsupervised field. And so the idea here is to try to improve the signal processing approaches by adding data, and try to improve the unsupervised methods by adding domain knowledge. Maybe I understood the mixing part differently, or does that answer your question?
Yes, partly, yes, but it's still two different approaches, two different methods.
Mm-hmm.
Can you do both in the same methods? Can you, in the same method, so maximize the sensitivity and under the constraint of controlling the probability of false alarm by normalizing the indicator as you did?
Yeah, I think the answer is there will always be a trade-off. So you can't have it all. I think I have a backup thing here. Yeah, so if this is the probability of detection on the y-axis and the probability of false alarm on the x-axis, and so we also have and this the point where we're operating is a choice, and I think the same idea applies to the methods we apply. We can choose, you know. If we want a high probability of detection, we have to make peace with the fact that we'll have lots of false alarms. And if we want very low false alarms, you know, then we'll have to make peace with the fact that we won't have that much probability of detection. And so I view these methods in the same way. If you are going to very aggressively regularize your unsupervised model, you might get a better or your method might be more suitable for correct detections, but as a consequence, you might get more false alarms. Yeah.
Yes, I understand this, but in the last, some of the last slides where you showed where you compared different methods, you also had different curves for each method.
Yeah, that's fair.
And so my question was more about this. What about having a kind of combined methods that could push the curve as high as possible?
So you, I don't think you're going to benefit from the mixing always of different methods. I can't. I should know this, but I looked into at some point mixing different classifiers, and you can gain something from that. It's close to you're approaching ensemble methods, so that's something interesting you can look into. But we were looking at an established method if you can modify it with your domain knowledge. As a contribution, but maybe it can be interesting to try to combine these approaches and see if you can improve your detection. Yeah.
Okay. Well, thank you.
Thank you very much.
I finished with my questions.
Congratulations on the research done and the nice presentation. Of course, as a PhD student, you do your research and you want to inspire the predictive maintenance area beyond the maybe specific applications you tested. And my questions are in that direction. Some of your methods, they worked well for outer raceway faults, but less good for other faults. So I was wondering, how well do your techniques generalize to other faults, like reduced smearing imbalance or other faults on the one hand, and to beyond rotating machinery, so the generalizability of your methodologies?
Thank you. So the methods will only generalize as well as, on the one side, the data you provide, and on the other side, the domain knowledge you provide. So if you don't account for the fault modes you described in your prescription of the domain knowledge, then you cannot expect your method to perform well. But I think one of the value propositions of, for example, adding regularizations to unsupervised models is that the unsupervised model on its own is capable of detecting any kind of deviation, whether that is a fault mode that you have not accounted for in your added domain knowledge. So even if you forget to add, to account for a certain fault mode, you would still perform reasonably, I guess, but you would not have the benefits of this specific, targeting a specific fault mode. Does that answer your question?
Yes. But that was also the reason why it didn't work for the other faults beyond the outer raceway fault in your, I think, chapter 6 or 5.
Oh yes. No. Okay. So in that case, it's kind of interesting. So you have some domain knowledge. You expect a fault frequency at you expect some increase in a certain fault frequency, but that is also an imperfect understanding of the world. That is a model of what we expect will happen. So you can prescribe all the domain knowledge in the world, but if your domain knowledge is wrong or not perfect, then it will not benefit your detector. So I think in the situation you described, the envelope spectra for the in-race fault didn't resemble the domain knowledge version of what we expected there, and then your results will suffer. Yeah.
Okay, thank you. In reality, you will, I guess, never have 50% of healthy data and 50% of faulty data, which was the assumption of your research, and which also allows using the area under the ROC curve as an evaluation metric. However, in reality, I would guess you have 99 or more % of healthy data and only limited faulty data. How would you, or can you explain what is the risk of the area under the ROC curve and how to do it better than using that evaluation metric?
Yeah, absolutely. Maybe I should just say for the audience, this the data sets we just described is for the test set. So we don't have any faulty data in our training. We only have access to reference data. But when we evaluate, it makes sense to have lots of data in the evaluation so that we can have a reliable estimate of the performance. So it's true that in practice, we will not necessarily have this nice balanced data set. But to be perfectly honest, we will also not have an ROC curve at all. Because to have an ROC curve, it implies that you have faulty data. So I think the ROC curves are very useful for this research, for comparing methods. But ultimately, in practice, you would probably be better off with something like a precision recall curve, or you would maybe settle for a certain, I guess you can even use something like the F1 score. I'm not sure if that's, sorry, I can't recall if that's influenced by the imbalance, but you should keep in mind that if your test set is imbalanced, so you have few faulty samples and lots of reference samples, then the evaluation you see might be lying to you, and you should keep in mind that you don't always have this luxury of a balanced test set. Yeah.
Yes, indeed. I think indeed precision recall are sensitive to the imbalance, so are more trustworthy. To further increase the trustworthiness, yeah, your research is based on the choice for deep learning and adding domain knowledge to these deep learning models. However, deep learning has the downside of being overly optimistic on its probabilities and so forth. How could you make that more trustworthy so that you can see the model, the context changed, for example, or you're evaluating out of distribution settings, the time varying conditions or different speeds of or whatever, so that the probabilities of your default deep learning model are not that trustworthy, and it might give a false sense of positivity.
Okay, yeah, that's. I think there's a very interesting research field in the supervised community where you do have access to faulty data, where people quantify the uncertainty of the predictions, and I don't know how that maps to the unsupervised problem that we're dealing here with, where we only have access to normal data. Because if we encounter these issues you just mentioned, for example, if the operating conditions changes or something else changes, typically you would employ an unsupervised method to detect that change and to know your supervised model is no longer applicable. So I don't know if you should have another unsupervised model to gauge whether your current unsupervised model is wrong, because that could just be a fault that you're missing. So I don't really know how you would quantify your certainty for the unsupervised model. But what I can say is that ultimately, when you have an ROC curve, it is telling you something probabilistic. It is telling you what is the probability that this fault I just encountered is an actual fault, as opposed to a false alarm. So that is the closest I think this research gets to quantifying the uncertainty of your predictions. Yeah.
Yeah, but it's not calibrated, indeed. Yeah.
If you don't have a test it, that's true. Yeah.
Okay. And of course, the holy grail is not fault detection, classification, but it's remaining useful life estimation. Do you think your methods could be extended, or the principles could be used to do a time to fault detection or remaining useful life prediction?
Yeah, I think the fault detection problem is especially interesting to me, because I think that is where the biggest bang for your buck is in terms of condition monitoring. But that's my opinion. I think when we get to remaining useful life prediction, often you sort of you have to trust a model in a very precarious time of the model, of the machine's lifetime, where it might fail. So that's why I'm more a fan of investing in fault detection than remaining useful life prediction. But that's not what your question was. So how can this fault detection is it useful ultimately? And the fact of the matter is, if you want to implement the remaining useful life strategy, you tend to start with health indicator, and then you do some fancy predictions on that. So I think that the health indicators that come from the methods we've developed here can certainly be applied in a remaining useful life prediction step. Yeah. Although maybe, sorry, the third thing I skipped over that you asked is so we don't do diagnosis. We don't do the identification of faults in this work. We do detection, and it could be interesting to extend this work in that way. One of the examples in this thesis tries to learn a latent representation where different fault modes are well separated, and that's maybe a good avenue to go to in that regard. Yeah.
Okay, thank you.
Thank you, Mr. Chairman. Thank you, Douw, for giving a very nice overview presentation. I still have a couple of questions. The first one relates to the online updating of the models. So you gave, for example, the car application. Could you elaborate a bit further on how do you see that in practice based on the models that you developed? So how could that be applied in practice, and is there a need then for updating of the models, or how would you implement that? Could you elaborate a bit further on that?
Yeah, no problem. So in this case, the application is collaboration with some of our colleagues at Siemens, and they have this problem where after you've produced a car, it can be defective. So it might have an annoying whistling tone or a booming sound that you encounter, and you don't want to sell that car to the client. So in this case now you would have an end-of-line test where there is a person in the car who checks if this faults are present or not. And an application for this work is to provide a more reliable way of detecting whether something is wrong with this car. Now, you mentioned that we might need to update the model, which is a valid point. So over time, either the cars might change slightly, and as a result, the data they produce might change slightly. And that means that our model trained on the initial data might no longer be relevant. And in that case, we need to schedule a regular sort of retraining of our model on a set of data. And this also relates to the question of Prof. Antuni. We need to carefully select the data that we consider to be in a normal condition. You know.
Then a second question relates to this Jacobian's regularization of the autoencoder, which seems to give some nice improvements for some of the applications that you have shown. Now there you think mainly in terms of performance towards interpretation of the model. Is it also leading to better interpretations in some of the applications that you mentioned?
I think in the
for example, for the features itself that you extract, is the interpretation of those features, is it more realistic, or is it easier to align with the domain knowledge that you mentioned?
Yeah, I think that's an interesting area of research. So this specific case I presented here, I don't think the features you learn are necessarily more interpretable in this particular case where we regularize the Jacobian. But in a different application in the thesis, we instead use augmented data to shape the latent representation of an autoencoder. And I think I mentioned this in the previous question. And there, the different directions in the latent representation correspond to different fault modes. And that brings a certain degree of interpretability, because if you notice, if you get a new signal, you plug it through the encoder and you see that it is moving towards what you expect from faulty conditions, then you can get some more confidence that this fault is associated with this fault mode. But it is not interpretability in the same sense that it is, that you can perfectly understand why the model is doing what it's doing. In that sense, we also have some work in the beginning of the thesis where we reproduce signal processing pipelines using deep learning building blocks. And there, the activations of the network that we produce have a physical meaning. So it can be, it is the energy in a certain frequency band, for example. So that's different kind of, and I know one is called interpretability and other one explainability, but I can't remember exactly which is which right now. Yeah.
Then I have last question. Maybe you could take back the slide 58 towards the end of the presentation where you were showing several pipelines. Yeah, this one. So you developed here these different pipelines for each of the different applications, which is nice. And then you have a parameterization that you make for each of those different cases. I was wondering, towards the future, do you think it might also be possible to come up with a more general theory that a bit application independent, that you could try to show what the optimal pipeline is, that you could maybe try to see what are the characteristics, system or data characteristics of a particular application field, and that you could immediately propose a kind of optimal pipeline instead of having to develop it per application. Do you think such a theory could possibly develop towards the future?
The thing is, I think the beauty is no, and that's what keeps us in business, I think. So the thing is that it will always be application specific, and the reason for that is that the optimal detector depends on the distribution of your faulty data and the distribution of your healthy data. So if you have a different application, then the data you're going to measure from that is certainly going to be a different distribution, and the detector or signal processing approach that is most suitable for that faulty and healthy distribution will be different. So I'm afraid you can have a general approach, for example, a strictly unsupervised model that will detect any deviation. That's general and will work for all problems, but it's not guaranteed to give you the best kind of performance. And for that, you need to think about the problem and model it properly, I think.
Okay, thank you very much.
Right, Douw, also from my side, thanks a lot for the very nice work. Now you brought something upon yourself, because generally we only ask questions about things that you present, which in your case could have been all about neural networks and stuff. Now you also talk about tire pressure monitoring, so that means I can also ask about tire pressure monitoring.
Fair enough.
So did you check how tire pressure monitoring systems typically work?
I was very afraid of this. No, I didn't.
So there's two different flavors of it. So there's a direct measurement approach, which is a pressure sensor directly on the rim. Or there's an indirect approach, which uses signals from your ABS sensors, wheel speed sensors. Now you say, okay, this sensor, I started the car and it was faulty apparently because it gave me a warning. Now, was it actually faulty?
No, but I guess in a tire pressure, it's well, in machines it's also complicated because there's varying degrees of faultiness depending on how flat your tire is. But well, at least for the purpose of my story, it was not faulty. I drove home and it was perfectly inflated, right? So maybe there was some I don't know, cricket that resembled ABS braking, and that triggered the false alarm. Yeah.
Do you have an idea what the temperature difference was in the desert when you arrived in the evening and when you left in the morning?
Maybe significant enough to change the pressure in the tire. Yeah.
So then now with all the stuff that you have, do you have an idea how you would improve these systems?
Well, I guess one way is to, in the same way that we measure operating speed in machines, you can measure the temperature, the environment, and adapt for that. So instead of doing order tracking to adapt for the operating speed, you can somehow train a model for each temperature, although I don't recommend training a model for tire pressure. Yeah.
That was going to be my final question. Do you suppose we change the existing algorithms by gradient-based neural networks and encoders, or not really?
No, I think that's a very important question. We should use the simplest approach for a problem. And I think the research we present here is we're sort kind of we're on the edge. We're trying to push the ultimate of the performance. But I think if you want to have reliable detection, you should start with your simple models, and you should keep the costs of different faults in mind. It's fine to have a fault detection, a false alarm on your tire. It's kind of annoying and it's anxiety-inducing, but it's much better than not being aware that your tire is flat when you're driving on the highway. Yeah.
All right, and maybe a final question for slide 62 and the slides before, where you compare the ROC curves for the different cases. I was now intrigued because I think the first case where your gradient enhanced method does well is a synthetic data set. I think this case is also a synthetic data set. And then I think the second case is a real data set. So is there something about your method that would work for some reason significantly better on synthetic data sets and not on real data sets?
Yeah, that's a fair point, and it also relates to what Prof. Van Hoek said, where your detection will only be as good as the prescription of your domain knowledge. So if we have simulated data, it's simulated, so that means we know the parameters for the we know the parameters of the fault parameters. So our domain knowledge can be prescribed exactly. But if we have experimental data set, there is no ground truth of how it's failing. And so that is why we did better on the simulated data set, because the domain knowledge we prescribed is sort of peeking behind the curtain. Yeah.
All right, thanks.
No problem.
Professor Julius?
Yeah, thank you. I had one also last question for that, Douw. Thank you for the nice presentation, the manuscript. So if we look back and in these methods, how mature do you feel that they are? So if tomorrow a spin-off company is made, would you put your money on these methodologies, or what else is needed to be done in order to put your money there?
Well, currently I don't have lots of money, so that's not a problem I'm facing. But no, it's a good question. I think you should always start with the simplest. You should start with the simplest approaches. So these kind of subspace detectors that we end off these linear methods, I would start with them in the company. Actually, before that, I would start with RMS and kurtosis. They're all good, indicators. And as soon as we've convinced the client that this condition monitoring thing is a good idea, then we can move to more advanced methods and win some probability of detection. But ultimately, this research was done for a reason. Like we show that if you have these fancy unsupervised neural networks and you add domain knowledge, the performance increases. So eventually, in this new startup of yours, it will make sense to move towards the more advanced methods that use these regularizations and so on.
Okay, thank you.
Is there any member of the jury who still has a question, as you can still begin at this point? Then I look at the audience. This is a public defense, so we welcome questions from the audience as well. No one, so I guess it was crystal clear, and now the jury will convene for the deliberation.